Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. Thank you very much for joining. And we have our week 11 session today, and it's a very important session. And unfortunately, because some of you are traveling, some of you are, but this way at least we'll have a recording of this session. It's in a way quite practical session in a way because it will touch some of you who will be working in this field. Okay, I'll tell you in a while, which would require the discussion that we'll have today, which is path planning. Now, one would say path planning is like a common thing, but it is important to know path planning for several reasons and several aspects, and that's why I found these slides very useful. I got it from a lecturer from Indonesia, and it is of two parts. The first part is what we will cover, which is related to our course. Second part is more related to the actual application. We'll see in a while. So the course is actually the drone flight planning or the path planning and principles and practice. So we will see which drone is capable of, and we have a special focus here. So we'll see which drone is more suitable for that particular focus. Why do we need the flight planning, the flight planning? So that's the why. Principle of flight plan design, how, and the software to perform drone flight planning, the what of this course, and of course some notes on safely flying a drone. So please keep this session as like interactive as we do in the class as well. So if there's a comment, anything, please feel free to jump in and have the discussion. All right. So if I before I proceed further, where do you think the drones are used the most, including everything, like including military, including civil, including hobby as well? Where do you think the drone is used the most, or for what purpose? Anyone?
Surveillance, I think.
Surveillance. So okay. Anyone else?
Inspection.
Sorry. Come
Inspection.
again? Inspection. Okay. Surveillance. So they're both in a way the same thing that requires a camera. Okay. And that's why even the hobby ones, even the hobby ones are using the camera. So the hobby ones are using aerial photography, video shooting, filmmaking. This is the hobby ones. But more than that, it is use the camera for other applications, including military for surveillance or surveying for civil engineering, and so many others. So the focus of today's path planning, UAV path planning, is what are the principles and practices for the imaging part, and how would you plan your flight, right? So, in terms of general selection, we know that there are two types of drones. One of them is a multicopter or a quadcopter, and normally hobbyists they use it, and it is a good, reasonable size, reasonable drone for small area mapping. And it is like it doesn't require much of a training. Of course, it requires training, but not much of it. And we can do high resolution. I'll tell you what's high resolution mean by the use of multicopter. Normally is the camera that we talk about for resolution, but the multicopter can take high resolution simply because you can stay at one place and take the image, and then uh, at the next place take the image. So you can slow down the speed of the drone, and the, the resolution of the number of images will be higher, higher number of the images in a particular speed. As compared to the fixed wings, it is also large scale map production. So this is used for the maps which could be for large areas. So if suppose you're talking about a football stadium, maybe quadcopter is enough, and probably a fixed wing is not enough maybe. But for like whole farms or cities or countries, you might need fixed wings or maybe satellite for that purpose. All right, some other applications are orthophoto mosaic development. If you take a closer look at, let me just zoom in a bit. You see that there are some part which are like torn in a way, but they're not torn. If you can see this part here, there are several rectangles there which are put together. Each of this rectangle is one image. Okay, and just like we do uh, the tiling of the floor, the mosaic of the floor, this is like having so many images put together, and this is how they build up this whole picture. So this is not one picture. All right. Then it could be used to develop a point cloud, which is to develop a 3D model. So not just looking from the top, but looking from the sides as well to develop this. So this is not an actual image. This is the 3D model, which is based on point cloud, a cloud of points. So each one of this picture is a point taken from the drone and deciding it to be its location. Another purpose is digital elevation. So this, if you take a look at it closely, this one and this one are the same thing. Okay. The difference is this is a normal image, an RGB, the red, green, blue, or the one that we take from a mobile phone, something. This one is taking the elevation, the heights of different points. So the highest point would be the dark red, and the lowest point could be the yellow ones. This includes the heights as well. So normally in the map, we don't see heights. It's a 2D map, but this one can generate in a way, have 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 the 3D information on a paper or on a slide or on a board. So to have a particular idea. So suppose if your drone is moving from here to here. If you let me just take a where is it? If I put the direction of the drone, for example, if it's coming like this, so it has to make sure that at this point it has to rise up so that it does not hit, or some other purposes as well. So this could be one of the application. Okay, so do we need flight planning? Yes, we need to make sure that our drones captures images at the right time in the right place. Okay, and we don't want to, and sometimes we cannot control our drones at all times, especially on larger areas or where we can't always see the drone. So we need to have a plan that will make the drone move autonomously. Imagine this one is taken by humans, like, so if let me zoom in again. Where is it? So the size of I don't have a pen here. Okay, pen. Oh, cannot. Huh? So it is a very small image here. Only this part is the image. That one capture. One capture only is smaller than this. So imagine taking so many pictures. So this itself could have thousands of pictures for this small region. So of course we cannot do this. So for that purpose, we need to have an autonomous path which is developed by something, and that can be used. And we want to make sure that the drone is flying safely as well, as I just told you about the heights and everything. So we need to have a plan so that the drone. So this is nothing different than the waypoints. The flight plan is basically defining the waypoints at the the 3 degrees of the 3 coordinates: longitude, latitude, and altitude all together. Make a set, and it is like a flight plan. You can stop me wherever you think you have a question. Please don't hesitate to ask. Okay. So in general, the short answer is to to do all this. To do all this, we need a flight plan. So just make a simple plan, which could be like this. All right. So this was the land that we want to map. Okay. So just make the drone move in a way like this, and it will give you the map. But it's not just about the area of it. It's not just the area or the rectangle that we're talking about, because of these peaks. These peaks here. From the top, it would look like this, right? It would look like this only, which could be deceiving if you want to have this. So you want to make sure the altitude is also considered in the flight plan. Okay, altitude to be considered. Why? Because In a 2D or just top of the image, we can just only see uh, one side of the picture, I would say. We don't get complete picture. Okay. Okay. A few things mentioned in this particular figure is forward overlap and side overlap. As the name says, forward overlap. Okay. So basically, if the drone is moving in this direction, for example, okay, it's like this direction. So this is the first image. And let me take another color so that you can distinguish. And this is the second image. As you can see that the green one is overlapping the red one. And there are a lot of reasons we'll see today, a lot of reasons to have this overlap. So this also has to be taken. So it's not just we take, suppose, 1 point here and 1 point here, maybe some points along this one here. And then since it is straight, 1 point here and 1 point here. And then again, make a U-turn like this. It's not just that. We'll see in a while that we need points in the middle as well for so many other reasons. And how far or how close they should be, we'll see in a while. All right, so let's start with a few things first. Can you figure out the differences in these images? It's not the exercise find the differences, no, but there are big differences in this image, in these images, especially in the first one, which is the first one here, and the last one. What do you think is the difference? Anyone?
It seems that on the left one, there's no building pictures, only the ground.
Okay. Okay.
Distance is the difference.
Come again?
Distance.
Distance means?
Far. The last one is far away from the from ground.
Okay, you mean the height?
Yeah, I mean the height. Yeah.
Height. Okay, very good, excellent. Uh, yes. So what Khalid noticed was that there's no picture because it is covering a small area. This one is covering a small area here. Okay. This one is actually only probably this part. If we notice, this is only this part in this one. So why is that? Because this image is taken from a higher altitude. This image is taken from a high altitude. All right. So the difference is altitude in this one. Okay. So what is the difference that is created because of the height? That, as Khalid noticed, that there are no buildings. So if you're looking for smaller region with more details within the region, we'll go closer. But if we want to cover larger area, we need to go higher. So this is actually higher. I hope I can write with the mouse better. This is higher and this one is not. This is low. All right. So what's the difference? The higher the drone flies, the larger the area covered it covers. So as you can see here, where is it? This is covering a large area. This is covering a small area. You can see that this is the comparison here. Okay. So if this was the picture taken at this height, this is slightly higher. So picture is slightly bigger, even higher. So now you can see that this house is appearing now. Even higher and even higher. So this is covering large area. Okay, so what is the cost? Higher area also means less photo for the same area. So if we are using this height, we need to, so if I say, take a look at this one, this image, this is one image covering the whole area. Okay, but if we were going for this height, this one, we need at least 1, 2, 3, 4, 5, 6, 7, 8, 9. So closer means we need to take more pictures. Higher, we need to take lesser pictures. So at least one thing that we we can say that at high altitude we can take lesser pictures to cover the whole area. Okay, in a way fair, but what is the cost? The cost is higher flight also means less details. Okay, it's very obvious. Something is, and uh, it doesn't have to be a camera. It has to be your eyes as well. In order to take a closer look to get more details, we have to get closer, right? So this one is, suppose for example, taking a picture of 3000 pixel and 4000 pixels, and whenever we see, since we'll be talking about images later on, so the images are defined by two dimensions, height and width. Okay, so this is height and this is width, and this is based on the drone's direction. If the drone is moving in this direction, then this is height and this is width. All right. Okay, so closer has more details. You can see that, you can see this yellow mark, something. But if you go far, you are still getting the same size of the image, but less details. You cannot see the yellow mark, which is here. All right, very difficult to see this one. So what is happening, that we are changing the ground sampling distance. This is in a way kind of an accuracy, or how good the image is. So roughly it can be defined as how big each pixel is on the ground. Remember the pixels, px is pixels. It meant something per inch, something, I don't remember. But on the ground is how much is the size on the ground. So that's why it is important to know that if I'm taking a picture of particular pixel, how much area or how much length and width or height or width it is on the image. So now we have to ask ourselves, do I need a detailed view of everything or just the global picture? And probably if we try to look at some examples, that where do we need the detailed view and where do we need a global picture? Can someone of you give me example, one of each? A detailed view, example for where we need a detailed view, an example of where do we need a global picture. What do you think? Anyone can answer.
I think detailed view if you are looking for something specific, searching for something,
Very
or
good.
the other view if we want maybe for highways, roads, something like this, obvious. We don't need the details on it.
Okay, I think quite good. Let me put it in a different perspective. For example, if there's a car lost, or no, so car or a human lost, and we are looking for someone moving on the ground. Okay, if you're trying to find if there, okay, let me remember during Hajj season, people try to cross the boundary and bringing illegally people from who are not having the Hajj tasrih. They bring, so now they're using the drones. So if they want to just detect if there's a car there, they can go higher to get a global picture, and of course something moving can be easily captured. But if they want to get the number plate, the license plate of that car, they have to go detailed view. I think this example is very clear now, right? Is it okay?
Yes.
All good, guys?
Yeah,
Any
yeah.
comment on this?
No.
All right.
Clear.
So moving forward, how to give it a number to this one. So assume that this is my drone, and this is optics, means the camera and the lenses are there. So this is it doesn't look like a drone, but this is the lenses inside. So that's why it is flying at a height of some altitude, and this lenses are having a focal length of something, and this is the imaging result, I would say. Okay, and now we need to find how much each pixel here reflect into how much on the ground distance, each pixel and the distance on the ground. So for the image that we get here, we need to see these few things. Okay, of course, the focal length could be adjusted. Let's say it is at 8.8. Sensor height is 8 millimeters. Sensor width is 13.2 millimeter. Image height, as I just told you, pixels, and image width, as I told you, in terms of pixels. Okay, so ground sampling distance, GSD, is a measurement of accuracy, as I told you, and the smaller GSD shows more detailed view. If it is smaller, this means there are more details. I just said for license plate recognition, we need to get more detail, so it has to be smaller. GSD value should be smaller. The formulas are very simple. Flight height, which is the altitude, sensor height, which is in this case 8 millimeter, focal length in this case is 8.8 millimeter, and image height or image width, which is 5472. So if I just put numbers here, flight height, just to give you an example, height is okay. Now height is, so for example, for a DJI Phantom 4 Pro flying at 80 meters, since it is the GSD is in centimeter per pixel, so everything has to be in centimeters. So 8,000 centimeters times sensor height, which is 8 millimeters, so 0.8 centimeter, and then focal length, which is 8.8, so 0.88. Can someone take out a calculator and give me the calculation, please? And centimeter, and image height 3078. Can someone give me the answer for this? Pixels. So you can see that 1 centimeter can go with 1 centimeter. Can someone give me the answer?
2.4.
2.4 or 2.36 centimeter per pixel. Very good. Excellent. Thank you. So this could be one measure of detailing. So which one is better? Smaller GSD is better to get more details. So if you want to get like even more detail, we need to get a smaller number than this, and we can adjust the focal length, or maybe, I don't know, the height or something, to get a more detailed picture. Each pixel in the image is representing 2.36 centimeter in real world unit. All right. Okay. Not just that. If you want to have a good seamless mosaic is like the tiles, and seamless means, you have seen when you have two tiles together, there's a line in between. Seamless, that this line is almost not noticeable. Have you seen wallpapers? The wallpapers for huge walls. The wallpaper comes in like rolls, but the rolls are hardly half a meter or 1 meter wide. They put one and then they put the next one together, but they match it so that there is no seam in between. That's similar thing that we're talking about. So if you want to have a good seamless mosaic, or a 3D model of area of interest, 3D model means like it's not just a top view but side view as well. We have to do something else, which is have to have overlap. I talked about the overlap before. We need to have this overlap. Okay, and this overlap is basically like this. So this is one image. When the plane is, suppose the red one, it is taking this image, this one, and when it comes to this place, it takes another image, but there's an overlap. You can see that this part is overlap. So how does it affect? And especially when I talk about the 3D model, just like when we like us being humans, we look in the front, our face looking in the front, we can see in the side as well. We can see the sides. We can have almost half hemisphere, half sphere that we can see. Same with the camera as well. The camera, of course, can see straight down, but can also see these lines as well. And these lines are actually angular. So it is taking the side view of this part. So that's why the camera might be here, maybe at this point, but it can look sideways like this as well. So suppose the camera was here and it is looking downwards like this, but it can also look here as well. Okay, and this will give us a side view. All right. So let me, okay, I think I can show you something. I was this morning watching, okay, what's next? Okay, let me finish this and then I'll go to a video. No, not a video, something that I saw this morning. Okay, so suppose assuming that this is the UAV flying at 1, 2, 3, 4, 5, 6 waypoints, and at each waypoint it is taking an image. You can see when it is taking at 2, it is overlapping. This much is overlapping. Okay, even the third one is overlapping with the first one as well. So there's an overlap. Okay, and this overlap results in images like this. So if you notice that that each image is quite this much, so this means one can go all the way probably here and all the way something like this. Okay, so going forward, it is having an overlap by 2 and 3 as well. And in this case, in this particular example, it looks like 60% overlap is there. 60% overlap between the photos, and this is the forward overlap. This is the forward one, and also sideways as well. Sideways, so between 20 to 40 overlap between the flight lines, the lateral overlap. Okay, now what could be a good overlap? That depends on, okay, once again, just to catch up, what are we doing? We are doing some imaging right now, but what is it to do with the flight plan? Exactly. Where do we move our plane and where do we start taking pictures? This is where the flight plan would be part of it. So a good flight plan should not have any gap between the images that we have taken. So there is not enough overlap. And this could be a good overlap, actually very good overlap, 75 to 80%. Very good. 60% is also not bad. Okay, but it could be excessive overlap. So if you start taking a lot of picture out of it, it will be a burden on the camera, the computation, and it might depend on a particular detailed view of something. But in general, 75-80% overlap is like already quite good enough. All right. So what's next? Yeah, this is another thing. So for example, this is a drone and flying at a particular height, and you can see that there are 60% front and side, both ways, front and side, both ways is like 60% overlap at 300 feet. Okay. This way, if these are the images, you can see that this one, this is one image, and then of course this is second one, this is third one, and this is the fourth image. You can see this region is having at least four images. Okay, at least 4 images in this case, which is good enough. All right. However, if we if we have a 50% overlap, let me say from the other side, it will have almost 4 images, most of the things. But this happened at the same altitude. Nothing changed. Altitude is same. But there is something like elevated here. And this elevation actually reduced the distance. The distance is reduced. I shouldn't have made this line. This distance is more than this distance. And if you go further, you can see that this is higher. So the distance is even lesser. The distance of the drone from the surface is even lesser. So this that 30% like overlap is there. 30% overlap. This is not because of the height of the drone, but the height between the drone and the surface, not the actual altitude of the drone. So that's why it is important. So if I go further higher, so not higher, but these are higher than the ground as well. So there's 0% overlap. You can see that there's this part is missing. This part is missing. Okay, and you can see that this results in 0 images of some things. So what to do in this case? What is the issue? Issue is that the distance between the drone and the surface has reduced, not the altitude. Altitude is still the same. They're all at the same altitude. All right, but this distance has reduced, which is to be taken care of. So in the flight plan, we need to see that if this distance is decreased, it has to go up like this, and then go like this higher, and maybe even higher for these situations. Otherwise, you can see that there is no stitching. What is stitching? That we put the images together and we stitch them, and just like we put two pieces of cloth and we stitch them, we put two pieces of images and we stitch them, and it is a proper software, actually algorithm, that matches that. Just like we do the jigsaw puzzle, we pick up the pieces and we stitch them together so that they are matching. The same thing happens when we put the images together to make the map. All right, and if we, yeah, so far so good. Any question? Let me show you something which I just noticed this morning. So you must have seen the maps. Let me share this screen now. Where is Chrome? You have this one. Okay, I'm opening a maps, and just you must have seen that this. Where are we? Somewhere here. Where's the tower? Let's go to the tower. The tower is here. KFUPM. Why can't I find the tower? Is this one? No. Must be here. Yeah, this is the tower. Okay. Now this is the tower, and when I move left, right, something, it still gives the same view. Even if I click the 3D, it's like just giving you the impression that it is 3D. Okay. If I move on the other side, probably, but still, I don't get more. I cannot see what's on this edge of the tower. Okay. Let me take you to Australia. I was watching the cricket match this morning and they were showing something. So I thought, let me try. So this is Melbourne, and the match was happening this morning here, cricket match. And I just tried to, go closer, and you can see the difference. Can you see the difference in this zoom and the other zoom? Look at this tower. Look at this this light tower. This is a light tower. Okay, I'm going closer. You can see the side as well, and actually you can look on the side of the tower as well. If I turn it, I have to zoom out maybe a bit. I can see inside as well, almost, which was covered before. Let me go further in detail. So you can see that now I can see this side as well. What I was looking at was one of the tower had a number. I thought, let me try to identify if I can see that number. This one, yeah, I think it was number 3 that I was looking at. Is it number 3? I think this is number 3. Or maybe this one. Yeah, this one, number 3. They were showing this tower. Oh, this number 1, sorry. So this is number 2, I believe. Not very clear, but number 3 was very clear. Yes, you can see this one, number 3, right? So this means it's not just because it is in Australia and it's very clear. They have moved the drone in this region very like so many times. So not even just here, but also here as well, on this side and all the sides. So like even Burj Khalifa is not like this. Let me show you the Burj Khalifa as well. It's not that good as this one. Where is it? Can't even figure out where is the Burj Khalifa. Where is the tallest shadow? Ah, this one. This is the Burj Khalifa, right? So if I press 3D, nothing happens. You know, there's not much except for this angle maybe, which is I think the natural angle. It doesn't give much information what's happening on this side, but for that one it was done. Anyways, let me share again the other. Where is it? Share this one. Any question about this particular thing about having a 3D model? As you can see, the Burj Khalifa, I cannot make a 3D model from the images, at least which is on Google Map, but I can make the map of Melbourne Cricket Ground because it is having enough images over there. So, okay, where was I? I was lost in something else here. Okay. Next is, yeah, one more thing. If so far it was just a map or something, but now if you want to register a real world coordinate, which is the longitude and latitude, just like this one, or we want to have actual measurements attached to it, then we need more calibration according to the ground measurement and the GPS on the drone. So we need ground control points. Control points, these are fixed points that we know of. Okay, and there are something like this on the ground. You might or might not have seen some some of this point, and these points could be identified from the drone. Okay, so these are the points on the ground visible in the drone photos and are defined in a reference system before or after the flight. So once we have it or before we put, okay, this point or this mark is this longitude and this latitude. Okay, so this is you might have seen guys suppose standing like this with this one. They're not for the drones, but they're doing surveying for uh, the terrain. You know, you must have seen, you know, let me just put terrestrial surveying method. Okay, but this have a mark so that it can be seen from. So this yellow thingy, as I mentioned before, is actually a ground control point which the drone can identify and has specific coordinates attached to it, so it can relate to the other points around it. So this will give you more accuracy in terms of that. Of course, the drones have GPS. Most of the drones have GPS, you know, but they don't have that accurate one. Okay, so without the GPS, of course, not possible. If there's no GPS, there is no recollection of where was this image taken. But with the GPS, we have a good idea. To have more accurate one, we need to either have the ground control points or accuracy of the onboard GPS to be increased. Any questions so far? All right, so this is a typical flight plan for, let's say, this is the area of interest to be mapped. Okay, so these are the waypoints that we discussed before, and looks like this is a flat surface, so there is no change in the altitude, but there could be a change in the altitude, and this is the direction of the drone. Okay, so at each waypoint, at each black dot, which is point of exposure, at each waypoint, it is taking an image. So at this red, suppose for example, it has taken this image. Okay, then again at this point, it has taken this image, and so on. like this. So it has a front overlap, and you can see when it was taking image, like this is going like this and then coming back like this. At this point, when the image was taken, there's a side overlap here as well. Okay, so like by looking at it, uh, what do you say about how much is the frontal overlap and how much is the side overlap? You can just guess by looking at the images or the waypoints. How much do you think is the front overlap and how much is the side overlap? What do you think, guys? Anyone? How much is the front overlap in this case? Overlap is basically how much the the images are overlapping the other one. How much the next one is overlapping the previous one.
10%.
Sorry?
10%.
10% frontal. I'm asking about the frontal one.
It is about 70.
70. Okay, let's take a look at this distance. This is one image, and this is the second image. Looks like it's 50%. I think it's 50%. 50, 60%. Actually, we can see that this image is falling on the other next waypoint. So this means this is 50%. This one could be maybe 20%, not too much. All right, so we can actually measure it, but just to get an idea. What happened? Can you see the screen? Yeah, okay. All right. So in short, we need to set the goal. What kind of end product do you want from the project or your drone experiment? Then we need to take into account a few things, which is, of course, the area, how much area to be covered, and the desired accuracy. So we need to know what is the GSD, the ground ground scale. This what was GSD? Ground. I forgot. Ground distance, ground sampling distance. I'm sorry. Okay. Okay. The height and the flight path. So the path is normal, but height needs to be taken care of because of the obstacles that could be there. Obstacles or the terrain changes over there. The ground control points for further accuracy. The overlap and side lap. Okay. Without the overlap and side lap, we cannot have the 3D shapes that we just talked about. Okay. So if you want to have a 3D model or 3D mapping, it needs to have a side and overlap as well. The type of drones, so looks like for smaller purposes, it could be a multi-copter or the other one is for the, and of course the regulations needs to be taken care of. Moving forward, suppose the project that I've given you, it is a very simple drone. Okay, if you need to map, give a flight plan to it, you need to enter the coordinates in the flight controller. So okay, go there, then go there, then go there. You need to enter in the code. Okay, but now they have apps for that. Okay, there's so many apps. For example, the Drone Deploy or Drone Harmony or Precision Hawk or maybe others that you guys know better. Those who are working, you might have seen in your own experience as well. So those can do a lot of things. What are those things? Quickly, let's take a look at it. They basically can design the flight plan based on the user input. So it can take elevation, overlap, distance, time. For example, you can see this one. It can take the front overlap, side overlap, direction, mapping speed, starting waypoint, the area covered, how many images, altitude, the resolution. This is the GSD, 4.5 centimeter per pixel, and it can avoid the obstacles as well. All of these things could be done so you can just put it in the software. It will automatically take it. So you just have to go and point or geofence the area. Geofence means that just give it the boundary and it will automatically do the flight plan. Other types of flight plan, especially for civil engineering or similar architecture engineering, maybe you need some time inspect or make a 3D model of something. So the drone doesn't only have to like go this way only, but also going around it at different heights so that it can take sideways pictures as well. Okay, and you can see that it is following the terrain as well. So if it is going down, it is going down, then again coming back up, and so on. So you can see that it started off like this, and then the next round it is higher. Next round it is even higher, and then going on the top to cover the top region. Okay, so this is for side inspections. The other one is if you want to see the side of some building or tower or something, that's called the facade, actually, the facade inspection. So this could be one application in which the drone just moves in two axes only. Let's say Y and Z, just Y, Z, Y, Z, like that. Okay, and it can map the whole side. Facade means side. That's not the facade fil ard, but the facade means the face. Actually, the face of it comes from that word. And similarly, it can also the software has a capability to identify one building. So if we click on one area, it would be able to identify this building is going until what end. So it is already mapping, this is a building, this is a building, or this is a building, and so on. It can detect all these buildings, and this can be on the OSM, OpenStreetMap data as well. So you can use you can import the map from the Google Street View and Google Street Map and use it with the drone. Okay, what's next? Yeah, the drones have the capability, the software has the capability to avoid the obstacles with a particular distance. So it can go around it or go over it to avoid the obstacle. I just wanted to show you one small video in which, this is 2017 by the way, but the obstacle avoidance and navigation was quite advanced at that time as well. So this is a drone which is flying without the GPS and maps. Okay, just visual navigation. Okay, it is using deep learning model in which it is based on the camera that is on board, and it is mapping what is around, right? Like while it is flying, not like following a map or model which was captured before. So this is what is looking at. It is looking that this is a where's my mouse? This is a safe passage, safe piece. There's no nothing in the front. It has learned, but it has learned that these things could be dangerous, so it's not going there. It is not going in these regions. So this green one is sorry. Where is my viewer here? So the green one is showing the safe passage for the drone. Okay, and it is done using the cameras on board. It looks like, even if you have we are flying, we can fly this safely, as this this drone is autonomously flying. Okay, a few things on since those who are going in this direction, so they can think of the drone as the flight plan. It can be done in the software, but it is important that the software is made. No, the flight plan is made in the software, taking care of the obstacles as well. Okay. Okay. This was the part one of the slides. The part two is those who want to go further in this area. So for the course, I'll pause here, and the rest is already in the slides that is uploaded on Blackboard. So to those who want to go further and do further in terms of the principle of 3D reconstruction, positioning the camera, and further about softwares and some limitations, they can go further in this these slides for their own knowledge. But I'll stop here for the course at this point. Any question, any comment?
Thank you so much.
All right, all right. So
Thank you, Captain.
thank you. I'll stop the recording here. And I'll quickly, where is it? Stop the recording. Quickly mark the attendance.